Hello all. It's been a really long time since the last time I uploaded an actual lesson, and this is a lesson from Unit 1. And as you can see in the title, we're going to talk about kinematic equations, also known as SUVAT equations among students. Before we dive in, I need to mention that these equations are really important because they might appear in your Unit 1 test, Unit 2, Unit 3, even Unit 4 or Unit 5 sometimes. I've seen questions related to the SUVAT equations. So I guess this is an important lesson. So let's dive in. So what's the general goal of these equations? So the goal, let's start with this. The goal of using kinematic equations, okay, is to determine any of the following physical quantities. And I guess I had to also say that kinematic equations are used to describe objects in motion. And as is often the case in even in real life, we are interested in figuring out how far an object will travel under some acceleration or deceleration, or what kind of speed an object will have if given some initial acceleration, initial velocity, and stuff like that. Okay, so the goal is to determine one of the following quantities. So the first one is S. Okay, it's a vector quantity and its displacement. Okay, displacement. Okay, and it's measured in meters. Okay, the displacement is a vector quantity because it also tells you the direction, like you also need to specify the position. Okay, U. Okay, I'm gonna actually spell out what SUVAT stands for. Okay, so U is the initial velocity. Initial velocity of an object. Okay, and as is the case with any quantity related to speed, the units are meters per second. Okay, V. Okay, is another quantity we are interested in, and that's the final velocity of an object. So final velocity of an object, also measured in meters per second. The other quantity we're interested in is the acceleration, okay, A, which is also a vector quantity, so acceleration, meters per second squared. So the acceleration appears as a factor that tells you how much faster an object, or slower, because so you can also have deceleration, okay? So it tells you how much faster or slower an object will be after some time passes, okay? So that's the acceleration, and okay, I will keep making an effort with my handwriting. Okay, so that's an S, so meters per second squared. I messed it up completely. Let me write it again. Meters per second squared, there you go. And the final quantity is time, T, okay? So time, and it's measured in seconds, and it's a scalar, okay? So I'm gonna write it here, scalar. It's the only one that is a scalar in the SUVAT equation. So from now on, I'm gonna drop, not from now on, I'm gonna keep, let me check my notes. Okay, at some point I'm gonna drop the arrows because usually using the SUVAT equations, we are interested in actually determining these quantities without caring too much about directions, okay, unless specified. And one last comment about time. Time is usually the time between two instances in time. Like we start with an initial velocity and we end with some final velocity. And sometimes we are interested in the time needed for that motion to take place, okay, for that change to take place. All right, so this is what SUVAT stands for. I'm gonna box it. Okay, so let's move on. Now, so it's really just 4 equations, guys, okay? And I will talk more about them. So, but first let's write this. So it's really just 4 equations, so not too many, okay? That you need to combine. Okay, to find what you're being asked for, okay? To find what you are being asked to find, okay? And it's really hard to talk about this here, so I'm gonna write it in parentheses, so more in past papers. So the SUVAT equations are the kinds of equations that there is not much theory behind them, but you need to apply them in real problems to understand how they work. So now I'm going to write down the 4 equations, and then we will move on. I will say a few more things and some examples, sort of. So let's write down the 4 equations. So equation, I'm going to make a table, and then I'm going to also write here quantity missing. Okay, and you will see what I mean in an instant. So S, we'll keep using arrows until we drop them, is U plus V over 2 times T. Okay, so using the initial and final velocity, I mean, this equation tells us that if we know the initial velocity, the final velocity, and the time needed for that change in velocity, we can determine the displacement, okay? What's missing here? The acceleration, right? We don't know the acceleration. Even though there was an acceleration, right? How do we know that there was an acceleration in this procedure? Because we started with an initial velocity, and in the end we have some different velocity, okay? So the only way to change velocity in nature is to give an object some acceleration, okay? Simple. Okay, let's move on. The second equation is V, okay? The final velocity is equal to the initial velocity plus the acceleration times t, okay? And what does this tell us? That if we know how much time passed between having an initial velocity and a final velocity, and if we know the acceleration that caused this change in velocity, we can find the final velocity, okay? What's missing here? The displacement, okay? And one more thing, okay, here we are using vectors still, okay? So in practice, I'm gonna write it and erase it. In practice, for example, in this equation, okay, if we don't write the displacement, sorry, if we don't use the vectors, we write it like this, okay? But it is implied that if we are dealing with deceleration, okay, we have to use this equation as u minus at, okay? So in this case, the object is accelerating, and in this case, the object is decelerating, okay? So, but let's move on. So this is what the arrow means. So the arrow introduces a plus or a minus sign depending on the direction of motion, pretty much. And this applies to acceleration. If we have acceleration, the sign is plus. If we have deceleration, the sign is a minus. And then for the velocities, you will have a minus sign if you're moving to the left, pretty much, okay? And a positive sign if the velocity is to the right. So, okay, this is the second SUVAT equation. The third SUVAT equation is given by S equals U times T plus 1/2 AT squared, okay? What does this equation tell us? That if we know the initial velocity and the acceleration of the object and the time elapsed between some initial velocity and some final velocity, we can determine the displacement. What's missing here? The final velocity, okay? Final velocity. Okay? And the fourth equation tells us that the final velocity squared is equal to the initial velocity squared minus 2 times the acceleration times the displacement, okay? And what's missing here? The time. Okay, what does this equation tell us? That if we know the acceleration and the displacement, as well as the initial velocity of an object, we can find the final velocity, even if we don't know anything about the time elapsed, okay? And these are the 4 equations. I'm going to show you, even though you don't really need to know this, but I think it helps with intuition. I'm going to show you the proof, like where do these equations come from, okay? So here I'm going to write proving the equations, okay? Because in physics and math, you can derive everything pretty much, right? From first principles. So, I mean, the SUVAT equations didn't come out of thin air. I mean, there is a reasoning behind them. So let's start with the first equation, okay? So the acceleration, and I'm not gonna be using vectors from now on. I think, let me check my notes. Yeah, I'm gonna drop the vector quantity. So the acceleration is defined as the change in velocity with respect to time, right? So let's assume that the change in velocity delta is equal to some final velocity v minus some initial velocity u, okay? So delta v is v minus u, and then this change took place during time which we call t, okay? So over t. So you can easily see that v minus u is at, or I'm going to come down here, v, the final velocity, is equal to the initial velocity plus a times t, okay? And this is our first equation, and okay, it's second in this list, so we derived that equation, okay? Okay. Let's now do a different thing, okay? So if, oops, I keep using the red. So if the acceleration, okay, if the acceleration of an object is constant, okay, then the average velocity of an object is given by v average equal to the initial velocity plus the final velocity over 2. Okay, but also the average velocity, okay, so also the average velocity is defined as the total displacement with respect to time, okay? So these two are equal, right? So we can immediately see that u plus v over 2 is equal to s over t, right? So s, the displacement, the total displacement is 1/2 u plus v times t, okay? And this is our second equation, okay? All right, so if we take now, okay, let's do one more thing now. So if we take equation, so EQN means equation, okay? If we take equation 1 and solve for t, we get, so v minus u over a is equal to t, okay? And if we plug if we plug, let's call this, no, I'm not gonna call that anything. So, and if we plug t into equation 2, we get s is equal to 1/2 u plus v, and then times v minus u over a, right? Or I can gather together, in the denominator I have 2 and a, right? So 2as, if I cross multiply, 2as is u squared minus v squared, right? So I can now solve for v squared to get v squared is u squared plus 2as. Okay, and this equation 3. Okay. Another thing we can do, okay, so far we have proved this, and this. So we are left with the with this equation. So how do we prove that? So also using, actually, let's write again using v equals u plus at, and plugging v into s equals 1/2 u plus v times t, we get s is 1/2 u plus at plus u times t, and my handwriting is incomprehensible, so let me write it again. So u plus at plus u, okay, times t, and then we just have to do the algebra. So we have 1/2 u ut, so I'm multiplying like that, and I'm also multiplying this, ut plus at squared, this is a plus and this is a t, okay, plus at squared plus ut. So this yields 1/2 at squared plus 2ut, and this is equal to ut plus, I don't know what happened to my page, plus 1/2 at squared, okay? So s is equal to ut plus 1/2 at squared, okay? And we have proven the fourth equation, okay? So this is how you derive these equations, okay? So they don't fall out of thin air, okay? And okay, this is all I had to say about how to derive these equations. Now I want to turn your attention into, when using the SUVAT equations, there is one more very important point that we need to clarify before moving on, and I'm going to write it here as a note, okay? So note, okay, the SUVAT equations often need to be used, equations often need to be used in 2 dimensions independently. Okay, so for example, when we have projectile motion, this is the case here, okay? So let's say we have some projectile that has some initial velocity u, but this initial velocity u makes an angle theta with say the horizontal axis, okay, then the SUVAT equations need to be applied in the x and y directions by resolving the vector, okay. So the x component of the vector is going to be ux equals to u cosine theta, and the subscript x means in the x direction, obviously, okay, and uy is going to be u sine theta, okay. And again, whatever touches the angle, okay, so the x component touches the angle theta, therefore we have a cosine theta, but the y component does not touch the angle theta, so we got a u sine theta, okay. So now the SUVAT equations have to be applied in the x direction, okay, in which we will have ux equals to u cosine theta, and the acceleration in this case is going to be 0 unless they specify something else, okay. And in the y direction, we are going to have uy, the initial speed in the y direction, which is going to be u sine theta, and the acceleration is going to be minus g, okay, y minus g, because the velocity vector points up, but the acceleration points down, okay, and the acceleration is g because we have gravity, right? Unless this is projectile motion in empty space, like maybe you take your Elon Musk's car and you venture into outer space, and therefore projectile motion does not involve gravity, okay? Maybe you're moving in interstellar space or something like that. But anyway, okay. Let's move on. So in my notes, I wrote it one more time. Okay, I'm gonna write it one more time. So vector resolution is what I have in my notes. So if, for example, they give us an initial velocity u that makes an angle theta with the horizontal, then the x component is going to be ux equals to u cosine theta, and the y component is going to be u sine theta, okay, which is uy. But they might also give us the angle with respect to the vertical, right? So maybe you have a situation like this, u, but they give you this angle, phi, okay? In this case, ux is going to be u, okay? This component does not touch the angle phi, right? So it's u sine phi. And now uy is going to be u cosine phi, okay? So, and I'm silently assuming that, okay, u is a vector, therefore u is the magnitude. Magnitude, okay, I'm sorry. U is the magnitude, okay, in what you see here, okay, in this page. Okay, now let's go back to the SUVAT equation. So back to SUVAT equations. Okay, I want to give you a few examples of motion. Okay, so let's make the following diagram. So SUVAT applies to projectile motion, right? Projectile motion, and but also in the motion of some object, okay, under some acceleration. Okay, so we have two cases, okay? So the first case is the vertical motion. And the second case is the horizontal motion. Actually, no, this is not the best way to put it. The best way to put it is that in any application of the SUVAT equations, we will have to independently deal with the vertical motion and the horizontal motion. Okay, now that's better. Okay, so let's go talk about various cases, common cases that might appear in tests. So case one. Okay, we have you have the case in which some projectile is fired with some initial velocity u that makes an angle theta with the horizontal. Okay, so therefore this component is u cosine theta, and this component is u sine theta, which is something we just talked about. Okay, so the projectile will generally undergo a parabolic motion. Okay, and in the most general case, this is the maximum height achieved, right? Max height, let's call it h. And another important quantity that needs to be determined in various problems is what is called the range. So how far it will travel in the x direction, pretty much. Okay, and okay, this is the x direction, I guess, and this is the y direction. Okay, so excuse me. So in this case, we naturally have a vertical component and a horizontal component. So let's go talk about the vertical component, or the vertical motion. Vertical motion. Okay, so we automatically know that the initial velocity, let's call it ux, uy. Okay, so uy is u sine theta. Okay, the acceleration is minus g. Okay, we know this a priori, because, which means from the beginning, because and the acceleration is minus g because this is I mean, this takes place on Earth, I guess. I mean, this projectile motion. Okay, so let's say we are interested in finding the maximum height. Okay, so this thing. Okay, so what do we have to do? So at maximum height, at max height h, okay, v is 0. The final velocity is 0 instantaneously, right? Because in the y direction, the projectile is going to have some initial velocity u sine theta, but the moment it reaches the maximum height, the final velocity is going to be 0 in the y direction. Okay, okay, and let me actually draw the scheme. So we start with u sine theta. Okay, and the object moves like this until it reaches the maximum height. Okay, this is h. Okay, so v is 0, and this is instantaneously. Okay, so which SUVAT equation is the best to use? Let's try. Okay, to find the maximum height, we need to know the time needed to travel from this position to this position. Okay, so how can we find that? We can use v equals to u plus at, or in our case, vy is equal to uy plus ay times t, where ay is the acceleration in the y direction, okay, which is g minus g, so ay. Okay, so let's plug in everything we know. The final velocity is 0, right? And this is equal to the initial velocity in the y direction, which is u sine theta, right? And then minus gt, right? So t is u sine theta over g, and this is the time needed for the object. Okay, let me turn a clean page. For the object to reach maximum height. Okay, but this is also the time needed. The time needed to reach half the range. Okay, we don't need this here. We don't need this information about the range here, but we will need it in a moment. You will see. Okay, so for the full flight, meaning all the way up and down, t total is 2 times t, or 2 u sine theta over g. Okay, now we said that we were interested in the maximum height. Okay, so the maximum height, okay, let me try to fix my handwriting. So the maximum height, the max height, h, is associated with the vertical, with the vertical motion. Okay, hence we can find it using v squared equals to u squared plus 2as. Okay, and let's call it this and let's call this vy, uy, ay, and sy. Okay, what's the final velocity at the maximum height? 0. What's the initial velocity? U sine theta, so we have u squared sine squared theta, and then we have minus 2g times h, where h is the distance, the displacement in the y direction. Okay, so h, the maximum height, after lots of calculations, is u sine theta squared over 2g. Okay, now let's go to the horizontal motion and determine the range. Okay, so for the horizontal motion, okay, we have ux, because now we are in the x-axis. Ux is u cosine theta. Okay, the time for the travel is 2 times u sine theta over g. Okay, the acceleration in the x direction is actually 0, right? Nothing accelerates the object in the x direction. And we need to find sx. Okay, so how can we find it? We can use sx equals to ux times t plus 1/2 ax times t squared. Okay, and we get this nice cancellation. Now sx is the range, right? So let's call it r, and this is equal to ux, which is u cosine theta. Oops, I don't know why I make these mistakes. So u cosine theta times t times and t is 2 u sine theta over g. Okay, therefore r is u squared sine of 2 theta over g, where I use the fact that sine of 2 theta is 2 sine theta cosine theta. Okay, so this becomes sine 2 theta. Okay, and this is I think the most complicated case that you might have. Okay, we have projectile motion in which the initial speed u makes an angle theta with the horizontal. Okay, and you will need to do a similar analysis if they give you this phi. Okay, but we don't examine this here, and I hope they don't give you something like that. Okay, all right. Another case is the horizontal projectile. Okay, so let's call it case 2. Horizontal projectile. Okay, so this looks like this. Let's say that we have a floor or maybe a cliff. Okay, so this is some cliff, and we fire a projectile horizontally with some initial velocity u, and therefore it's gonna undergo a motion that will look like this. Okay, and it's gonna fall to the ground. Okay, again, quantities of interest are the height of the cliff or whatever it is, maybe a tall building or something like that, and the range, okay? So the height is associated with the vertical motion and the range is associated with the horizontal motion, okay? So this is gonna be a little bit simpler. So for the vertical motion, we have a lot of information. We have that uy is 0. How do I know that? Because the projectile is fired with an initial velocity u in the horizontal direction. Okay, so vertically it has no component. Okay, so the initial velocity in the y direction is 0. The acceleration is now g. And okay, let's call it ay is g. And you might notice you might have noticed that I'm not using the minus sign here. This is because the projectile, if we come here, for example, okay, the velocity is tangent to this parabola, okay? So the velocity here at some instant v prime points down, right? So if we analyze it, it will have a horizontal component that points to the right and a vertical component that points down in the same direction as g. Therefore, because the vertical component of the velocity points down in the same direction as g, we use ay equals to g, okay? And okay, the displacement in the y direction is h. So what are the quantities we don't know about this motion? We don't know the final velocity in the y direction, and we don't know the time needed, okay? Okay, so are there any ways to figure this out? Yes, we can use the SUVAT equation vy squared equals to uy squared plus 2ay times sy. Okay, we get this nice cancellation because the initial velocity in the y direction is 0. And as you can see, as the projectile moves, its velocity in the y direction increases, okay? So and it's gonna be a maximum right before it reaches the speed, the floor. And this is the y direction, okay? So if we plug in everything we know, we find vy is 2gh, and then we need the square root, okay? So we found the speed in the y direction, the final speed in the y direction, okay? How about the time needed for this motion to take place? We can use vy is equal to uy plus ay times t. Okay, so vy is the square root of 2gh, vy is 0, ay is g, and t is t, okay? So the time needed for this motion to take place is the square root of 2gh over g. We can pull the g in the denominator into the square root by squaring it, right? G squared. So the time needed will be 2h over g. Okay, we analyzed the vertical motion for the case in which we shoot a horizontal projectile off a cliff or a building or something like that. Now let's go see what we can find from the horizontal motion. So horizontal motion. So for the horizontal motion, we now know that the initial velocity in the x direction is u, the acceleration in the x direction is 0, okay? We want to know the range, the distance traveled, the displacement in the x direction, but we now know the time as well, the time needed for the projectile to go from this position that I mark here with green to this position that I also mark with green, okay? And this is the range, okay? The time needed to do this is given by 2h over g. Okay. So how can we find the range? We can use Sx is equal to ux times t plus 1/2 ax t squared, okay? AX is 0, so we get the very nice cancellation. It's always nice to get cancellations. So, and SX is R, right? So the range is, Vx is V, and T is just the square root of 2H over G. And that's the answer, okay? All right, so this was case 2. Again, case 1 was the very general case in which we have a projectile fired under some angle theta. The second case was the projectile fired from some cliff with some initial velocity only in the x direction. Okay, let's go to case 3. So case 3, this is a free fall only downwards, to specify this, okay? Only downwards. My handwriting, I'm sorry. So only downwards. Okay, so what I mean is that maybe this is the ground, okay? And maybe I'm flying with my parachute or with my balloon or maybe with an aeroplane or something like that, and I throw something, okay? And I just throw something and it falls. Okay, so this is the case. So in this case, again, even if it starts from rest, and this is what we will assume actually, that we start from rest. So if you throw the stone and you start from rest, then you only have a vertical motion in this case, okay? So you don't have to deal with complications. So the initial velocity in the y direction is 0 in this case. Maybe we are interested in finding the final velocity. And we know the acceleration. The acceleration is g. Why is it g and not minus g? Because okay, the stone will start here with 0 initial velocity, but as it falls, its velocity is going to keep increasing, and the velocity vector points in the same direction as the acceleration, okay? Therefore, we use plus sign, a plus sign, okay? So to find the final velocity, you can use Vy equals to Uy plus Ay times t. So Vy is going to be simply g times t. Okay. We can find this height, let's call it y. Okay. We can find this by using Sy equals to U y times t plus 1/2 at squared. Therefore, y is 1/2 gt squared. Okay, and another quantity we can find, actually, sorry, we can also find Vy. So for these two equations, we need to know the time to specify the quantities needed. If we don't know the time, but they ask us for the final velocity, you can also use Vy squared is Uy squared plus 2asy. Okay, so this is 0. So Vy is the square root of 2gy. Okay, because ay is g, sy is y. So another way to find the final velocity, if we only know the displacement, is by using this equation. Okay, and this was case 3. Another case I thought about is the vertical throw. Okay, so let's do case 4. Let's call it vertical throw. Okay, in which case we have an object or a projectile going up and then down. Okay, and maybe you are down on the ground and you throw a projectile upwards, so it's going to go up, stop instantaneously, and then come back down. Okay, so in this case, the acceleration is actually minus g. Okay, and it's minus g when the object goes up, and then uy, okay, uy is going to be u, and maybe we are interested in vy and how far up the object will go. Okay, so, and okay, yes, okay, so we can use vy equals to uy plus ayt to find that vy is uy, we call it just u, and then minus gt. Okay, so this is going to be the final velocity if we know the time and so on. But we can find the time needed for the object to go all the way up. How can we do that? By simply observing that the final velocity at the maximum height is 0, right? So time needed for the object to go all the way up can be found by observing, by observing that at the maximum height, the maximum height vy is 0. Okay, so by using this, we can find that 0 is u minus gt. So I took this equation and set vy equals to 0. Okay, so the time needed for the object to go all the way up is t equals to u over g. Okay, and okay, this is an important thing we can find. Okay, determining the time needed to go from this position that I mark with green here to all the way up. It's an important quantity because if we multiply by 2, so 2t is the time needed for the full motion, up and down. Okay, and I'm gonna close up this video by saying that we can find the maximum height y, right? So let's say that they ask you to find this. Okay, so we can use as y is equal to uy times t plus 1/2 ay times t squared. So y is going to be u times t minus 1/2 gt squared. And if we use the t that we just found, we can write u times u over g minus 1/2 g, let me see, g u squared over g squared, and this g cancels. So we have u squared over g minus u squared over 2g. So the maximum height reached is u squared over 2g. Okay, but be careful, you have to use the time needed for the object to go all the way up. If you use 2t, you're gonna reach something weird, I guess. Okay, so let me box this. Y is u squared over 2g. Okay, so the maximum height reached depends on the initial velocity and g, which makes sense, right? And I'm gonna stop this video because I think it's too much information for one video. I want this video to be only on SUVAT equations because this is of interest to students taking Unit 1, but they might also appear, I mean, the SUVAT equations might also appear in Unit 2, Unit 3, Unit 4, Unit 5, Unit 6. And I'm pretty sure they can appear in the Edexcel exams for the UK, which are slightly different, which have a slightly different material than the international Edexcel exams. But I'm pretty sure they use the same SUVAT equations. And in any A-level tests, these equations apply and are used. So I hope this video is useful and it reaches the right people. Let me know what you think about these videos in the comments, like, subscribe, and see you in the next one.